Welcome to the chapter on the reinforcement function of geosynthetics. The reinforcement function is defined as the use of the stress-strain behavior of a geosynthetic material to improve the mechanical properties of soil or other construction materials. This definition primarily refers to reinforced soil structures and the base of embankments. The problem with soils is that they have a limited angle of repose related to the friction angle and cohesion of the material, which can lead to failures if a soil slope is oversteepened, overloaded, or the strength reduces due to groundwater changes. The conventional solutions to steepen slopes or create vertical structures to change ground levels whilst minimizing land take would include reinforced concrete cantilevers, board-piled or sheet-piled retaining walls, mass retaining walls such as gabions, masonry, or crib structures. All of these structures are externally stabilized, with the structure working to restrain the soil pressure and require an exponential increase in the stiffness or weight of material to resist the loading as the height of its structures increase. By contrast, reinforced soil structures are internally stabilized. By layering grids or textiles within a fill body, the self-weight of the fill soil and any surcharge applied generates a tension in the reinforcement. This hybrid mass of soil and reinforcement transfers the vertical loads through the soil, and rather than generate lateral expansion of the soil block, instead generates tensile forces within the reinforcement, which act as an internal confinement. Put simply, the layers of reinforcement add the tensile resistance that the soil is lacking. The hybrid mass of soil and reinforcement will act together as a gravity retaining wall to retain the unreinforced soil behind, and must resist sliding failures, overturning failures, tilting and bearing failure, and global slip circles. Any facing applied to reinforced soil structures is purely to provide an aesthetic finish and prevent localized erosion or unraveling of the face. Facings consist of vegetated steep slopes, gabion finishes, modular concrete blocks, or concrete panels. Since the soil and reinforcement work in harmony, the increasing cost with increasing height is relatively insignificant, making extremely high structures more feasible. Internally, the reinforcement is designed to ensure each reinforcement layer has sufficient strength to resist rupture and that there is sufficient pull-out length at each layer. In comparison to externally stabilized solutions, the reduced volume of steel and concrete, together with the reduction in site deliveries, serve to reduce the embodied carbon content of the site. This is particularly notable where Site 1 fill can be reused within the reinforced soil structure, further reducing import and disposal costs and traffic. Reinforced soil solutions are typically far quicker to build and significantly cheaper than externally stabilized solutions, and improve constructability, making greater heights and construction on poorer foundation soils possible, whilst also providing a wide range of aesthetic finishes to suit the project requirements. A brief case study on the first use of reinforced soil slopes on the UK motorway network. From 1994 to 1996, the first widening of the M25 motorway to 4 lanes was carried out on the southwest corner of the M25 between Reigate and Heathrow. The typical cross-section required around 4 metres cut into the toe of existing side slopes, which consisted of very poor London and Galt clays. The conforming reinforced concrete cantilever solution needed to be deep due to global stability constraints, which in places cut into water-bearing gravel layers, posing further problems. Alternative solutions, including soil nails and reinforced soil slopes, were considered. The reinforced soil slope solution was considered the most cost-effective, but due to concerns about the lack of experience on UK motorways at the time, it was decided that on the first contract between junctions 15 and 16 at Heathrow, the clockwise carriageway was to be widened using reinforced soil slopes, and the anti-clockwise using the conforming reinforced concrete cantilever retaining walls. This provided a unique opportunity to view the two solutions side by side in almost identical situations. The depth of foundations on the reinforced concrete cantilever necessitated sheet piling and dewatering to facilitate the casting of the cantilever sections, whilst imported fill being placed behind the walls when they were eventually backfilled. Due to the shallower foundation and speed of construction, the reinforced soil slopes were able to reuse the Site 1 materials. This side-by-side comparison highlighted the benefits of the reinforced soil solutions, including the reuse of the Site 1 fill material, the reduced depth of the foundation works and subsequent safety improvements, and significant reductions in both construction time and costs. Further guidance on the design and execution of reinforced soil works is available in the list as follows. Another source of information on all matters geosynthetic will be to join the UK chapter of the International Geosynthetic Society. We have a dynamic student membership, which is also free for students in the UK. It gains you access to leading geotechnical journals and conference proceedings, and the chance to put papers and academic research into upcoming geotechnical conferences around the world.